Hello everyone, and welcome to this webinar for Scia Engineer 15. My name is Dominic Piepers, and I work as a customer service engineer for Scia. The purpose of today's webinar is to give a little bit more explanation about a new feature in Scia Engineer 15, namely the composite design. First, I'm going to start with a short explanation about how things work. In your GoToWebinar, you can arrange the sound settings in this window. Next, if you have any questions, don't hesitate to enter them in this question box window. We will try to answer them immediately after the webinar. If there are a lot of questions, they will be answered afterwards by email. And of course, this webinar will be recorded, so you can watch it afterwards again, or on our website or on our YouTube channel. Here you see the content of today's webinar. I'm going to start with a short introduction about Scia Engineer in general and about the new release Scia Engineer 15. Next we go and have a look at the composite analysis model, the so-called CAM model. How should you model this in Scia Engineer, and what about the finite element analysis? Then we're going to continue with the composite beam design, which checks are possible in Scia Engineer 15, how to perform them, and which settings are important for these checks. Next we're going to have a look at the Autodesign function, on which way can steel profiles be optimized. And of course we're going to end with a short conclusion and the questions and answers. Scia Engineer uses the latest technology for modeling, analyzing and designing all types of structures in different types of materials, like concrete, steel, aluminium, timber or composite. It's a powerful CAD-like modeling tool with advanced analysis capabilities such as dynamic calculation, construction stages, pre-stressing, second-order calculation, and so on. There is a comprehensive support for Euro codes with national annexes, and also a wide range of other design codes such as the US code, British Standard, the DIN code, and so on. There are also some BIM possibilities. Scia Engineer is certified for IFC. There is a BIM toolbox, and there is an intelligent link with Tekla and Revit. Here you see some examples of the modeling with Scia Engineer, including all types of beams, plates, shells, and full 3D solid modeling. Here you can see some example of results from different analysis types in Scia Engineer, like dynamic calculation, stability calculation, the linear and the nonlinear one, pre-stressing and construction stages. There's also a possibility for multi-material design. We have steel and aluminium code checking, steel connection design and its code checks, reinforced concrete design of beams, plates and shells, timber member design and code checking, and now also the composite design and code checking. At the end of every analysis you have the possibility to use automatic or customized calculation reports. There's also a possibility to create automatically some drawings with the overview drawings. There are a lot of possibilities to link Scia Engineer with other softwares. Since Scia Engineer is IFC certified, there is a link between CAD, BIM and MET software. There is also the BIM toolbox, with which structural models can be converted into analytical models. The XML link gives you free access, input and output to object data, and for users with specific calculation sheets there is the Excel link. As mentioned before, there's also the intelligent link with Tekla and Revit structures, and last one, Scia Design Forms. With this tool you have the link to our own created Scia Design Forms, or you can use the already developed calculation forms, or you can create new calculation forms yourself. Shortly we released the new version of Scia Engineer, namely release 15. Here are some new functionalities, like new concrete design to the Euro code, the composite floor design, which is a topic we are going to discuss today, plastic analysis of steel plates and shells, and there are a lot of usability improvements, and there is the open design. Next we're going to start with the topic of today, the composite analysis model, or the so-called CAM. This model contains composite beams that comprise a heavy gauge steel profile, a concrete deck with or without reinforcement, shear connections between steel beam and the concrete deck, and a corrugated steel sheeting that serves also as formwork for the wet concrete during the stages of construction. In practical and Scia Engineer, this means that if you want to use the composite analysis model, you have to use plate with ribs or rib slabs. There are composite decks and there are metal decks. A composite deck has two layers, a profile steel sheeting and a concrete topping, reinforced or not, and a metal deck has only one layer, the profile steel sheeting. This type is mostly used for lightweight roofs. The development of the CAM model or the composite analysis model has a lot of advantages. Mainly, there are no longer load panels needed to distribute the load to the beams, and also no simplified assumptions are needed regarding the load distribution. Complex geometries of the composite deck can be taken into account without simplification assumptions, and the in-plane stiffness of the deck is automatically calculated and taken into account, as the deck is modelized as a structural member. So, also no additional simplification assumptions are needed in case of horizontal loading of the structure. Now, if you want to use this composite analysis model in Scia Engineer, the only thing you need to do is to use both of the materials, concrete and steel. There are no additional functionalities needed. The two available codes for the check are the ECEN, the Eurocode, and the American code, the IBC. Now, to model ribbed slabs in Scia or plate with ribs, you have several possibilities. Or you can draw a plate and afterwards insert the ribs, or you can directly draw a ribbed slab. Third possibility is that the beams are already drawn and you can insert the plate afterwards and connect them with connect members and nodes. I will quickly show this one in Scia Engineer. I already modeled a simple structure as you can see in here, and as project data only material concrete and steel are used, the Eurocode as the code, and no additional functionalities are ticked on. Quickly going to change the view like this one and only show the first level like this. Now you see the beams are already been drawn, so actually the ribs are already been drawn. Only thing I need to do is to add a plate, and here if you now draw a plate, if you have used the concrete and steel material in your project, you directly have the possibility to change the analysis model for your plate. You have the default one, standard one. You can use only a metal deck, as mentioned it was for instance lightweight roofs, or the composite deck directly. You choose a material and to give in a thickness. I will quickly draw the plates and also quickly insert an opening in here. Opening in this plate, yes, like that. So now I only insert the plate, and the members have not yet been connected with the beams. So with this option I can quickly connect them, and I take this one on, connect 1D members as ribs, and as you now will see, he has connected them all. And I will quickly use this view. You see in here, this is the effective rib that he is going to use. This is not the one he's going to use eventually, because eventually he's going to do an automatic calculation of the correct effective rib. You also see that here, also next to the plate, the effective width is shown. Okay. As we have just seen in Scia Engineer, for the plate properties you can choose between a metal deck, a profile steel sheeting, or a composite deck, a profile steel sheeting and a concrete topping. A composite deck is modelized as a multi-layered plate. Each layer has orthotropic properties, and the eccentricity of each layer is taken into account. Next, the stiffness determination is done by layer, meaning the bending and membrane forces, and afterwards at the end the stiffnesses of both layers are combined together to become a general stiffness for the composite deck. The interaction of the layers is considered as a perfect bond, so without any slip between the concrete and the steel sheeting. The strains are determined from the displacements and rotations at the nodes of the finite element mesh. Now, the assumption of perfect bond is definitely reasonable for the longitudinal behavior of the composite deck, meaning in a direction parallel to the corrugation. In the direction perpendicular to the corrugation, this seems less obvious. However, the stiffness of the sheeting in that direction is very low and will hardly influence the behavior of the composite deck. Therefore, that approximation of a perfect bond is acceptable. Here you see the plate properties actually. So the plate parameters for the concrete sheeting, and you see the local coordinate system which is going to be used in Scia Engineer. Now, as mentioned before, first every layer, the stiffness of every layer is calculated. So first profile steel sheeting on its own, we have a bending stiffness and we have a membrane stiffness. Of course, the calculation of these orthotrophic plate stiffnesses will be done by the use of the modulus E, modulus G and Poisson's ratio of steel. A detailed information can be found by using this link to our online help, where every parameter is described in detail and every formula is described in detail. Now, as mentioned before, the profile steel sheeting is a plate property, so also this has to be chosen in the properties of the plate itself. There's also a library available in Scia Engineer with predefined steel sheetings. So if I go back to my Scia Engineer and I select the 2D member that we just created, here you see the property profile sheeting. You have the possibility to or create a sheeting yourself, and here this one is ticked on automatically, so this means that the orthotropic parameters will be calculated automatically. Capital D are the parameters for membrane forces, bending forces, and minor d are the parameters for the membrane forces. There also is a library available in Scia Engineer with all these profile sheetings already in it. This one could be easily copied into the project and can be used. So also for this plate I'm going to use this one from the profile library. Say okay, and now it has been changed. You also see the material has also automatically been changed. Now the concrete deck, that's actually the same. So it's also an orthotropic concrete deck. So also bending stiffness and membrane stiffness has been calculated. You see the C and from stiffness from the concrete. Also here the same, the modulus E, modulus G and Poisson ratio are used for the concrete stiffness calculation. If the stiffness of both layers has been calculated, they can be combined to become a general stiffness for the composite deck. Of course, proper rotation of the matrices must be applied before combining the layers, in case the orientation of the steel sheeting does not correspond to the default coordinate system. This is done by the angle between the principal orthotropy direction y, in the direction of the corrugation of the steel sheeting, and the default non-rotated local y-axis of the 2D member. In Scia Engineer it's given by the local coordinate system rotation angle in the 2D member properties. Now, if everything according to the plate has been set in by the plate properties, also the beam properties can be chosen or has to be chosen to have a correct calculation of the composite analysis model. In the context of composite structure, there are currently three possible types of behavior of plate ribs in Scia Engineer. The first one is without composite action. This is meant for beams that are connected to the deck without shear connectors, so the deck is just lying on the beam. There's actually no composite action in that setup. This is modelized by a plate rib without eccentricity. The second one is with advanced composite actions. In this case, a perfect shear connection is assumed between the beam and the deck. The plate rib is modelized with its wheel eccentricity. In this configuration, axial force will appear in the beam and membrane forces will appear in the deck. The diffusion of the membrane forces in the deck will be automatically calculated by the finite element modelization of the deck. The internal forces for the composite checks later on will be obtained by integrating the obtained stresses in both the steel beam and the deck. And the last one, with standard composite actions. In this case, by default, also a perfect shear connection is assumed between the beam and the deck. The plate rip is modelized by a beam without eccentricity. In order to take the composite action into account, the stiffness of the beam is adjusted to take into account the effect of eccentricity and the participating width. In the same way as a so-called advanced model, the internal forces for the composite checks will be obtained by integrating the calculated stresses in both the steel beam and the deck. Now in Scia Engineer, I already modeled the plate, but actually I haven't changed anything about the ribs yet. So I will select one rib, and as you can see, by default it is set type of connection user defined eccentricity. So I'm going to select them all with the same property. And here now you can choose between those three types: without composite action, no shear connection between; with advanced composite action, with a perfect shear connection; and with standard composite action, also with a perfect shear connection between the two. Now the next step is actually the effective rib. Here you see shape of rib is T-symmetric, so actually you have the possibility to insert the effective width yourself. But there is also the possibility to let Scia Engineer calculate it automatically. That you can do by choosing here the option automatic. By choosing automatic, these parameters width on the left and width on the right are grayed out. So you see, yet there have been no changes done. If I'm now going to launch the linear calculation, it's quickly done. It's now calculating the internal forces in the ribs. Yes, I accept the results. And now you will see, if I take again a view on top, that the effective width has been changed. Previously it was 500 millimeters. If I select just one, you see that now it has been changed into 638 millimeters. Now how is Scia Engineer going to calculate this effective rib? Scia Engineer is going to calculate the effective width according to the following geometric rules. Parameter L is the span length of the considered beam. Parameter A is a configurable constant, which is by default taken equally to 8. This corresponds to the specification of the ISCI IBC code for the effective width in the analysis model. B adjacent left and B adjacent right are the maximum values of effective width on the left and right hand side due to adjacent entities. The effective width on a side may not exceed the distance to an edge of the slab or half of the distance of the adjacent beam. The distance to the adjacent entity is calculated at mid-length of each member. The effective width is calculated as a uniform value for each member. Now this parameter A can be changed in the solver setup in Scia Engineer. So if I go back to Scia, setup and next solver, you have here this parameter span length ratio L divided by B effective max for automatic calculation is equal to 8. Another important setup for the automatic calculation of effective width is this one, parallelism tolerance for automatic calculation. It is set by default equal to 10 degrees. Next, the shear connectors. By default, the first shear connector available in the shear connector library in Scia Engineer will be used automatically. Of course, this can be changed or overruled by using composite beam data in the composite menu of Scia Engineer. So if I go back to Scia Engineer, first of all, in your libraries, here you have shear connection libraries in the composite menu. If you go to shear connector, this one is the one that will be used by default by Scia. Of course, here you have the blue file to insert shear connectors using from the library. So by default the first one is used. Next, in the composite menu you can change this by adding composite beam data onto the member. For instance, if I select one, you see here this type of shear connector will be used. If I click on the three dots, I can change it and I can use, for instance, this one from the shear connector library. Next, the different load cases in this CAM model or composite analysis model. Construction stages has to be taken into account in analysis of composite structures, mostly for two reasons. First, the profile steel sheeting is used as a formwork for the concrete topping, so it has to carry only the weight of the concrete. And the second one is that the behavior of steel and concrete are fundamentally different. Keep in mind, for instance, the stiffness is different, effect of creep, and so on. In general case, construction stages are taken into account in a simplified way, by calculating each load case in the stage corresponding to its assumptions. In Scia Engineer now there are three different stages. First we have the construction stage. In this stage, only the steel and the composite decks are enabled. Concrete has no stiffness and its self-weight is carried by the steel structure, so the profile steel sheeting and the steel beams. By default, only the self-weight is assigned to this construction stage. Second one, the final stage long term. In this stage, the composite decks are enabled. The concrete stiffness is reduced to take into account the effect of creep under a long term of loads, and by default again, in Scia Engineer all permanent load cases are assigned to the final stage long term. Third stage, final stage short term. In this stage also the composite decks are enabled, but here the nominal concrete stiffness is used in order to take into account the short term loading. And again by default this contains all variable load cases in this final stage short term. In the standard composite analysis model there are now three different construction stages for the entire structure. There is no such thing like stages for casting of concrete or staged building for steel structures. It is however planned that this will be supported in a later version. Now in Scia Engineer, if you create a load case, if you have enabled the CAM model, first one is the self-weight and it is automatically put into the construction stage. Second one, a permanent load case into final stage long term, and the third and the fourth load case are variable load cases and automatically assigned to final stage short term. Of course, you as a user has the possibility to change these load cases from one stage into another. Of course, for the final stage long term, the effect of creep has to be taken into account for the concrete. This is done in Scia Engineer by reducing the E modulus and G modulus of concrete. The EC0 and GC0 are the values from the material library. Next, an additional parameter KE is calculated to become a reduction of EC and GC. Of course, this reduction factor KE is 0 for the construction stage, meaning that the concrete has no stiffness at all. For the final stage short term, this parameter is equal to 1, meaning that creep has not been taken into account and there is no reduction of the stiffness or no reduction of the E and G modulus for the concrete. Of course, for the final stage long term, the creep coefficient is taken into account and you will have a reduction of the E and G modulus. The creep coefficient itself is defined in the composite setup and it counts for the entire structure and is applied to all composite checks. Now in Scia Engineer, in this composite menu, under composite setup, this is a general setup that is used for the entire structure. Here you can say if you want to take creep into account, yes or no, and you can fill in the creep coefficient, which is equal to 2. This one are the default values, so if you change something you can always go back to the default ones. Optionally you can disable this creep coefficient, take into account creep coefficient by setting here no. And this means that the load cases from the long term stage are moved to the short term stage during the calculation or the analysis of the project. Here you can see an overview of all available checks in Scia Engineer 15 so far. So for the Eurocode 4 composite beam checks, we have the ULS construction stage check and the ULS final stage check. For the American code, 36010 ASD and 36010 LRFD, we have both checks construction stage final stage ULS and construction stage final stage SLS, which are the checks for the deflections, of course. Here you can see the composite service tree in Scia Engineer. On the right you see, of course, it starts with the composite setup, which you can see in this picture. This composite setup is used for the entire structure. There are some of the properties that can be overruled by inserting composite beam data on a certain member or on a set of members. This one I will immediately show directly in Scia Engineer. The same for this one. As mentioned, some of the parameters that are available in the general composite setup can be overruled by composite beam data on a member or on a set of members. For the load cases and construction stages, also this can be viewed in this composite service menu. Here you see that the load cases are automatically stored in the correct stage. So the self weight is for the construction stage. All the permanent loads are going to be assigned to the final stage long term, and all the variable loads are going to be assigned to the final stage short term. Okay, the checks itself in Scia Engineer. So if I go to the composite service, here you have the composite setup. This is the general setup for the entire structure, for the entire project. This one, which is in the analysis model, this one will be taken into account by the solver, so this is the one that will be calculated. Here you can choose whether you want to take creep into account, yes or no, and you can give in the creep coefficient. Additionally, you can also say that the composite beams are propped, meaning that the steel structure is propped during the hardening of concrete. So actually you will delete the construction stage, and also the self weight or the load cases that are in the construction stage will be moved to final stage short term or long term, depending on the creep parameters in this composite setup. And of course the default degree of connection for beams with composite action is 100% in this setup. Next is shear connectors. Here you can also say how many connectors per row you want to insert, how many rows per span, what is the placement, transfer spacing, and so on. So everything about shear connectors can be inserted here. The shear connectors itself can be overruled by composite beam data on the 1D members. Some default configurations about the slab reinforcement, so longitudinal and transfer reinforcement, and some default parameters for the deflections. If you change anything, you can always go back to the default ones by clicking on this default button. So that's the first thing. Second thing, in this one, load cases and stages. Every load is assigned to its correct stage. You can easily change it, for instance like this, and if you're not sure, you can always go back by clicking on automatic, and Scia Engineer will automatically assign the correct loads to the correct construction or calculation stages. So self weight construction stage, permanent loads final stage long term, and variable loads final stage short term. Next we have here the 1D members. So here you have the possibility to insert composite beam data. Composite beam data, for instance, as already mentioned, used to overrule the settings for shear connectors, slab reinforcement, and deflections. I have not yet calculated, so I have no results in here, so I cannot perform the check. I will quickly do the calculation, the linear one. At this point, only the linear calculation or the linear static analysis is supported by the composite analysis model in Scia Engineer 15. In future versions, also other calculation types will become possible, like for instance the dynamic calculation, but at this point of view this is not yet possible, so it is under construction. Okay, now I have calculated. And now I have the possibility to do a construction stage check and a composite beam check. Quickly going to show this one here. Here you see in Scia Engineer in the composite beam design or composite analysis model, we have three different type of output levels. We have the brief one, which you can see in here. It's very briefly one table with the unity check. The table with every check itself, sorting in a unity check and a status, okay or not okay, and a very detailed output with really every detail, every formula, every parameter printed in this detailed output. So in this model, I insert a model like this, so with several stages, and I'm only going to perform the check for this level, so that's the one I'm going to show like that. Going to start with the construction stage. So in this stage, the self-weight will be checked. I'm going to perform the check for a safe selection. I already saved a certain selection. Going to regenerate that check, and first of all I choose for the brief output to start with. So performing the check for 66 members, and you see the highest unity check is here, this member 0.44. If I have a look at the brief output, you will only see, because I have chosen the extreme value as global, one extreme value, unity check 0.44 for beam 82. A little bit more in detail is the table output, because in the table output you will see every check that the engineer has performed for the construction stage. So you see shear buckling resistance has not been performed, but status is set to OK. Vertical shear resistance check has been performed, 0.12 as unity check, and the bending moment resistance is the highest one, 0.44. Also, the LTB, lateral torsional check, has not been performed. If you want to see why, or if you want to see the check itself in detail, you can always have a look at the detailed output. So I will regenerate again. And here you see now, if he's done, yes, a very clear, detailed output of the construction stage check. First of all, everything about the geometry. So the beam itself, the concrete and the steel sheeting. It's a continuous beam with a length of 7 meters. Every parameter is printed here in detail. Cross-section parameters and material parameters. So it's an IPE 220, material S 235. So everything is printed out here nicely. If he knows the cross-section and material properties, there is a possibility to perform a cross-section classification. Every formula is printed out in detail, as you can see in here. Every value is filled in to become a classification for the flange with class 1 and for the web also class 1. So the cross-section in total is classified as being class 1. Next, the design value of the loads. So actually the loads, I have a moment and some shear force. Partial safety factors that will be used, and starting from chapter 5 the actual check will be performed. Everything before chapter 5 is actually data in the structure. Cross-section data, material data, partial safety factors and so on. So the first check he's going to perform is a shear buckling check. Certain conditions has to be met to perform the shear buckling check, and as you see in here, the shear buckling resistance of the web does not need to be verified. So that's also the reason why, and I'm quickly going back to my table output. Yes, that's also the reason why here the shear buckling resistance, there is no value printed and the status is automatically set or printed as OK. Going back to the detailed outputs. Okay. Chapter 5 we were. Okay, shear buckling check. So this one does not need to be performed. Vertical shear. Of course this one is performed. First of all, the shear area is calculated, parameter AV, according to the code of course. The check has been performed, and the shear resistance check for vertical shear is a unity check of 0.12. Next, the bending moment. The influence of the shear of the bending moment resistance may be neglected as printed in here, because of the real shear force is not larger than 50% of the plastic shear resistance. If it would be okay according to the code, you have to do a reduction of the bending moment, and Scia Engineer will also calculate this reduction factor. The moment check itself, classical moment resistance, gives a bending moment unity check of 0.44. And the next check, LTB resistance or lateral torsional buckling. Also, this check does not need to be performed because the steel sheeting is connected to the steel beam by tough decking, welding of the shear connectors, and provides continuous restraint to the top flange. So actually the LTB resistance or lateral torsional buckling resistance does not need to be checked. And at the end, the summary, okay, the ULS check for the construction stage is okay, and with a maximum unity check of 0.44. Okay, that's for the construction stage. Now the composite beam final stage actually. For the final stage we also take into account the concrete, because for the construction stage we only have steel and the weight of the wet concrete, so no concrete stiffness. For the final stage check we also have the concrete stiffness. The principle is exactly the same. I'm going to do the check for, I'm going to start with my name selection, brief outputs, and we generate the check. See, global value is printed in here, 0.29. So what I'm going to do is only select this value, current one, and I have now unit check of 0.29. In the brief output, you will see again very briefly in this beam I have unit check of 0.29. A little bit more in detail is the table output, because here is printed out which code is used for which beam and which checks are executed. So in this case the vertical shear resistance and the bending moment resistance, and the bending moment resistance is the one that gives the highest unit check of 0.29. There are also some warnings printed. Warning are information for you as a user. If there is an error, of course, you need to make sure that this error is solved before you can execute the check itself. Okay, the detailed outputs. The first part is exactly the same as in the construction stage output, meaning first geometry data, everything is printed again in detail, cross section and material parameters, still the same as before because it's still the same cross section and the same material, cross section classification, again web classification of 1, flange classification of 1, so cross section is classified as class 1. And now of course also concrete slab with profile sheeting. So also for the concrete slab now the parameters are printed because we are now in the final stage check. Height of the slab, material of the concrete slab, parameters of the profile steel sheeting are printed in detail in here. And the parameters for the shear connectors are printed. You see it's SH1 with all the parameters printed here. What is the material? Parameters of the reinforcement that has been used is in the composite setup. Design value of the loads, and last chapter of the data, chapter 4, are the partial safety factors. Again the same, starting from chapter 5, here the actual check will be executed. I'm not going to discuss every check in detail, it's just a copy of let's say Eurocode 4 that has been implemented in Scia Engineer. I'm just quickly going to overview them. So first, shear connection. What is the design resistance of the shear connections? And he's going to start with shear connection in a solid slab, PR solid of 113 kN, and shear connection in a profile sheeting, which is 79.2 kN. Here you see a warning printed, same as in here. So actually this is also very some nice information for you. If there is something wrong or there is a warning or there's some information, it is always printed out in this detailed output. The calculation of degree of shear connection. First of all, calculation of effective width. Because we have determined in our beam properties that we want Scia Engineer to calculate the value of the effective width, he's going to do this calculation automatically doing the linear calculation, of course, and the calculation will be printed out here in this output. So you see here a nice picture. Calculation for every side, left side of the beam, right side of the beam. And eventually you will have an effective width of 812 millimeters. Next, the minimum degree of shear connection is calculated with a parameter eta minimum equal to 0.4. And then actually the real degree of shear connection will be calculated. First, tension resistance of the reinforcement. The Fs value is calculated. Resistance of the shear connection is calculated, NC parameter, and tension resistance of the steel member is calculated, which is printed out in here. Minimum 1 will be used, and you see here now, okay, eta equal to 1, eta minimum degree of shear connection is 0.4, so the shear connection degree is adequate or sufficient, so printed out okay. Cross-section resistance of the composite beam. As you see, the top flange is restrained laterally by the slab, and therefore only cross-sectional resistances need to be verified. Again, shear buckling, same as before. It will be checked if it is necessary to perform the shear buckling check, yes or no, and in this case again, shear buckling resistance of the web does not need to be verified. Okay, continue to the next one. Vertical shear, also same as before. Shear area will be calculated, parameter AV. Shear check will be performed, and this one results now in a shear force check of 0.16. Now for the bending moment, of course, first the center of gravity has to be calculated. And you see here that now the E modulus EC effective has taken as half of ECM. Next, the center of gravity YD is calculated, as you see in here. The degree of reinforcement is printed out in here, very in detail. And also, as a conclusion, the longitudinal reinforcement of this section is adequate. Check for the moment resistance. First check in the moment resistance is it needed to perform a reduction caused by the shear force? No, in this case again it's not needed. A negative bending moment resistance calculation has been performed. You see every detail printed out in here with some nice pictures. And this gives now a plastic moment resistance of 139 kilonewton meters. Next, the design moment resistance is calculated. And of course this gives now a unity check of 0.285 or rounded 0.29. So this one is okay, again okay. Longitudinal shear, so the transfer reinforcement has been calculated or has been checked, and also this transfer reinforcement is adequate, so also sufficient for the check of this beam. So here you have now ULS or final state check is okay with a maximum check of 0.29. So these are the two checks that are possible for the composite analysis model according to Eurocode 4. ULS check construction stage and ULS check final stage. In this PowerPoint again a small overview of the three different types of output levels. We have the brief one, only one unity check value. We have the table, which you have a unity check for every check or verification that has been performed. And we have the detailed output where everything, every formula, every parameter will be printed out. Here again an overview of construction stage check and final stage check. Now Autodesign. In Scia Engineer you also have the possibility to perform an Autodesign or to optimize your profiles automatically. Actually Scia Engineer itself will search for the steel profile which is the nearest or give the unity check nearest to 1. So you have this button here in the action window, Autodesign. It's for the final stage check and also for the construction stage check. So let's say I select one in the construction stage check. I'm going to say current. He has a unity check of 0.44. If I click on Autodesign now, this button, there will be a message popping up. The filter will be switched onto cross section. Here this filter was set to no. This Autodesign option you have to do it cross section by cross section. So I say okay, and I will choose the IP 220 because that's the one I'm going to Autodesign now. Click again on Autodesign. And this window will pop up now. In this window I have a maximum unit check of 0.439. And here you can give in the maximum value you want to reach. So you can give in 1 for instance. So now Scia Engineer, if I click on search for optimal, will search for the profile with the unity check nearest to 1. So you see in this picture or in this window that he is changing in the background the profile or the cross section. Now keep in mind that this is just a simple auto design. This means that he's going to use the active internal forces in that member. Meaning actually he is changing this profile now. He has changed it into an IPE 180 AA parameter. But he has still used the self-weight, the stiffness and so on of the IPE 220, the profile which we started with. So actually, if I click now again OK, and again we perform the construction stage check, I have 0.95. To be 100% correct, of course, I need to take into account the correct stiffnesses and the correct loads, or the self-weight for instance. So I'm going to recalculate the project quickly. Calculating the internal forces in the ribs. Yes, and then again I can perform the check and see if it's still okay. Now you see I still have 0.95, so okay, it's still okay. Good, so that was a bit all about the composite analysis model in Scia Engineer 15 and what is possible so far. So we can perform the check, ULS construction stage and final stage, and we have the Autodesign function to search for the most or to optimize every element in the structure to have unity check nearest to 1, to have an economic design of your structure. So the conclusion. First of all, we have seen that using the CAM model or composite analysis model is very easy. It's just with the basic functionalities of Scia Engineer, and you have to model a rep slab. Take on the material concrete and take on the material steel, and that's all. Then you can use the CAM model or composite analysis model. One of the advantages is that Scia Engineer is now correctly calculated the in-plane stiffness of the composite plane, meaning that there is no load panel needed because you are physically modeling the concrete slab with the steel sheeting. And the loads are automatically assigned to the correct stages, so self-weight construction stage, permanent loads final stage long term, take creep into account, and the variable loads final stage short term without taking creep into account. We have until now the composite beam checks according to Eurocode 4, ULS check final stage and construction stage, and according to the American code, ULS check final stage and construction stage, and also SLS check final stage and construction stage. We have seen that we have 3 different types for the output: the brief one, the table one, and the very clear, very detailed output actually. And we have the possibility to perform an automatic optimization of the beams. So that's it. That's it for the composite analysis model so far in Scia Engineer 15. Thank you for attending this webinar about composite analysis model. Please, if you have any questions so far, don't hesitate to insert them in the question box of the GoToWebinar window. We will try to answer them immediately. Due to the high amount of attendees, it's possible that we will not be able to answer all the questions right now. If that is the case, we will create a list of the questions and answers and we will send them to you afterwards by email. The next webinar will be about steel connections, and this one will be given in September. So again, you can, a few weeks before the start of the webinar, you will receive a registration link on which you can register yourself for free. Please, if you have any questions, don't hesitate to contact or your local sales representative or email sales@sciaonline.com, or for the support questions, email support@sciaonline.com. Thank you.